Yes. Are the slides visible? Hello, students. The slides are visible to all of you. Yes, students. Hello, hello.
Yes, sir, visible.
Oh, but why it's so much of delay, phase delay? Maybe you can call it little bit of response. I thought. I mean, so many students are in the class. Probably very few you can say respond. I don't know. What's the matter? Anyway, it's really cold morning here also, and think at your place also. But uh, what we discussed on the last turn was about, you can say, jamming process, and jamming, you can say, how it can be you can say made more effective, and how spread spectrum signals avoid, or you can say deceive the jamming process, you can call it. So that's, I hope, I mean, all of you have at least understood it. Then there was some issue about near far problem. I think near far problem is a problem of, you can say, spread spectrum system based systems. You can say any mobile service operator who is providing, you can say, spread spectrum based, mobile services, technology based services. Those particular, you can say, cells, or you can say mobile cells, they face this problem, near far problem. What is a near far problem? You can say a person who is near the base station, if he also transmits the same power as a subscriber, which is, you can say, maybe a kilometer, 2 kilometer away from the, you can say, base station. So I mean, the power level, you can say, or the interference that this particular person who is just, close to the, you can say, base station will produce for the other users. That means I talked about multi-access interference, MAI. So obviously, a person who is nearby the base station should transmit less, you can say, power, and the person who is, at a distance from the base station, he should transmit more power so that his signal reaches to the base station in a recognizable form. So this near far problem is there in, you can say, in a spread spectrum system based. Of course, the solution is, you can say, uh, carried out by, you can say, having some power control mechanism. What's a power control mechanism? Power control mechanism is, you can say, the base station communicates with the subscriber and tells that you are transmitting more power, and there are some, you can say, automatic, you can say, some, you can say, fields which take care of this power, you can say, how much power is appropriate depending upon the channel conditions. So these power automatically reduce the, we don't even know about, or subscriber even doesn't know that, this process is going on inside his mobile. So the power, any subscriber who is nearby the base station will transmit, automatically the power is reduced to reduce the excess interference. So this is the near far problem, at least, which, is a problem as far as direct sequence spread spectrum system are concerned. Now, multipath fading, what's the meaning of fading? जैसे color fading होता है ना, it's something, signal can also fade. What does it mean? Signal fading means the signal amplitude is, you can say, gets reduced, and gets reduced so much sometime that the call is dropped. So this, why this fading happens? You can say the fading is variation of the signal amplitude at a particular place without any movement of the subscriber or movement of, you can say, any other. So what are the reasons for that fading? Fading, I mean, that basically in very elementary form you can understand it, that the signal in free space is coming through different paths. There may be some line of sight path, there will be some, reflection paths from, you can see, some buildings or some cars or some other trees or anything. You can say the signal is reaching to the user with a lot of paths, and when these particular, you can say, signal amplitudes combine together at the base, user subscriber mobile, then obviously they may produce, you can say, very high constructive interference, or there may be, you can say, destructive interference. That means the signal amplitude will obviously will be reflected as an addition of these particular signals. So that's a multipath fading, I mean, because of the multipath, and multipath is you can say, very, you can say, you can't, avoid multipath in wireless media, because once the signal is transmitted from the base station, which particular path, where it meets, where it gets reflected, scattered, or anything, that happens, you can say, in free space. So this fading, how this is relevant to spread spectrum system, we'll see that. Now, it is a phenomena where signal is starting from the source like different paths through various refractions to reach the destination. As I explained, at destination, we have some total of various versions of the signal coming via different paths with different attenuations and delays. You understand? If a signal is passing through a tree, or a signal is getting reflected from, you can say, a building, or maybe a passing car reflection, maybe from a passing car, you can say, or any other, reflection, you can say, that may happen. And because of that, because if it's a multi-part, transmission, then there will be delays also, because some you can say paths will be taking more path length than the other one. These attenuations and delays again change due to change in refraction index of propagation media and change of reflecting surface. So these also add up. Reflection from a moving vehicle. From our discussion of the techniques in this section, we can find that delayed version has low autocorrelation with original signal. Okay, understand? Autocorrelation, very well. So if the delay is more, the autocorrelation, you can say, will be poor, you can say, corresponding. And whole spread spectrum recovery is based upon, you can say, autocorrelation or cross correlation concept. So that's a big, you can say, issue here. More so, if the delay exceeds chip duration, if the delay is so much that, it exceeds one chip duration, then it is treated as interfering signal and is rejected in the same manner. So that will be considered rejected. I mean, obviously that signal you don't want to put inside your mobile, and perhaps, at least combine that, because that is obviously interfering signal. I mean, if you are trying to decode, let us say, 100th bit, and your 101st bit is mixing with that, that means it will be problem. However, a better method is available today to utilize power available in the signal coming from multiple paths. Okay, that's very interesting also. Key, like, how do you utilize it? And this is used in many applications. This is a completion rake receiver. Very good. This, which is a bank of correlation receivers, is correlated to delays adjustable of different arriving paths. Finally, the output of the correlators, which are coherent, are added with improved reception quality. So look at the technology, you can say. Understand? Technology, how, I mean, you can, of course, I mean, this is about ranging, but how technology has, you can say, enabled this rake receiver. What is a rake receiver is? It, you can say, little bit of, you can correlate with FM also here, because the sideband powers get added up with the main power. You can say that we talk in as why FM is better as an analog system. So rake receiver, at the receiver side, you have at least, let's say, 4 5. The rake receiver may have 5 fingers, 4 fingers, 3 fingers. I mean, that depends upon the design. You might say that why not have, let's say, 10 or 20 or 30, maybe, I mean, as many paths as perhaps we can handle. But this becomes very difficult. Even if you can have 3 4 paths added in a same phase, obviously your signal strength will be, you can say, very much enhanced, or at least will be improved. So this rake receiver, this is used in all, you can say, mobile system based upon a spread spectrum, and that the region, you understand, at least why we are trying to improve upon the signal power. Or signal to noise ratio is obviously, that is determined, you can say, the quality of the signal, or even for data also, you can say. Now, this is one of the rake receiver. Rake receiver, maybe I'll discuss later on, I mean, about, you can say, major form of it, but at least this is sufficient for you, at least to you understand this concept, rake receiver. Then comes the ranging application. Okay, what is meaning of range? You understand? Ranging means essentially how far it is. So suppose, I mean, I'm let's say at a height of 1,000 meter, or I'm at a height of 2,000 meter, or our pilot is at a height of, you can say, I mean, 10,000, you can say, feet or meters, or so that a particular height, how do you range it up? In fact, you can understand it like, even in airport, you can say this, while aircraft, you can say, movements also, they know that how far the you can say particular plane is from the, you can say, airport. So how do they calculate this particular, you can say, distance? They calculate based upon these kind of ranging, you can say, methods. So they can get, you can say, a very good idea about. And particularly nowadays, this accuracy has to be there, ranging. Particularly, you can say, just look at, at least its other applications. Like, suppose you have enemy target. Now, enemy target, if it is moving also, let's say another aircraft, fighter plane, let us say, how do you range it up? Unless until you know at what height it is operating on and with what velocity is moving on, you can't do anything. And we have seen it, like, I mean, so accurately people are, you can say, aiming on those targets and destroying those targets. So that's what, you can see, the technological advances that perhaps have been obviously over the years coming up. So how this particular, with a this ranging application with direct frequency spread spectrum, how does it happen? Let us say, if I transmit from, let us say, this station T1, and there is some aircraft, let's say it is my radar or any other application. Now the signal gets reflected from the, you can say, this object, and I receive, you can say, T2. So I calculate this delay, you can say, how much delay it is. And then this particular delay I multiply by this, and I have low pass filter, and then I get GT minus T1 to 2. So, I mean, this is the signal, let's say, depending upon these delays. This particular signal that I'm, my GT function, it gets delayed. And what I do here is, I have this particular, you can say, input through integration through some, our chip duration, we can decide about, you can say, whatever the corresponding voltage V0, what you can say, I integrate it from 0 to LTC. And then what I do is, I have adjustable delays. I try to adjust if, the delays are properly, you can say, estimated or not, and then again fade to the particular system. So depending upon, you can say, this particular delay, if I can calculate them nicely, I can make estimation of the particular, you can say, distance or range. I think range applications, I suppose, the many such application you can see in, radar also. I mean, you can say the traffic control also, you know up to kilometer or 500 meter, they can have a range of, you can say, they can they can identify a particular motorcyclist or, some car who is, moving at a higher speed than provided as per the law. So a particular range is, defined for them. I mean, like, how far they can be effective. So this again a application of ranging, how distance, you can say, how far it is, and that it is within the particular equipment operating or not. So this is a very, I think this particular ranging is very, very useful in, you can say, many applications which you can name also, like, in your GPS systems. You can, if you suppose someone is lost somewhere, and if you can trace him out, that what is his GPS location. Nowadays people are providing GPS location or through WhatsApp, I mean, where you are standing on. So you can easily, it's so accurate, this particular, location identification. That's based, again, GPS is a spread spectrum signal. So it's a really, in a way, very, very, you can say, useful technique to be used for our civil applications also now. This is what we can, you can say, mathematically, at least understand it. If suppose this is my signal that is reflected from the intended target, and T1 T2 seconds later on, this how the signal will look like, you can say, what kind of signal I am receiving. Now alpha represents my signal attenuation in free space, how far it is. Theta is the random phase caused by the time delays. Okay, the carrier, this is determined using a squaring circuit of equivalent, and then the PN sequence of GT minus TT is extracted. The PN waveform having been recovered is correlated with the waveform GT minus DT, which is a PN waveform delayed by known time interval. Okay, this correlation function RGT, which is the output V0 of the integrator. So you are correlating with a, you can say, another given delay, you can say, particular, signal, and this is negligibly small if the difference in the difference it delays, that means D minus T1 T2 exceeds the chip duration. It will be very small, you can say, RJD output. And if this is maximum, when D is equal to T, I mean, this particular delay D that we are trying to correlate it, if we can calculate it nicely, then I can produce the V0 output as, very, you can say, very good, you can say, amplitude signal, which will be obviously useful for me to determine it accurately. And then I can define distance d c by 2, d plus minus 1, you can say, corresponding to tc. V is the velocity of light, and t1, t2, the corresponding chip duration, you can say, for plus minus tc. T1 is equal to T2, I presume that what is the transmission will be equal to, you can say, corresponding to the reflected signal. So you understand the basic principle of range application using spread spectrum signaling. The another example of, you can say, spread spectrum system is frequency hopped spread spectrum system. This is another category of the spread spectrum system, frequency hopping. Now, frequency hopping as the name you can understand, hopping means what? A monkey hops, you can say. So it's something like your spectrum signal hops. I mean, you can say at one instant you are transmitting, let's say at 1 megahertz, carrier. Another time you can maybe at 1.5 megahertz, or maybe 1.6, or maybe 1.9, or maybe 1.3 again. So you are hopping from one frequency to another one. That's a basic name. Why is this frequency hopping? And those of you who are using Bluetooth, this particular technology, that's a very good example of frequency hopping spread spectrum system. And you can understand it, why Bluetooth is operating in this particular band, you can say 2.4, or 2.5 gigahertz. Hey, any student knows about it? Why, you can say, Bluetooth technology is, operating in this particular frequency range? And who has, decided that it should operate at this particular frequency? And why? Maybe possible reasons. Yes, students? Any student? Hello? Any response? By my voice is audible or not? Hello?
Yes, sir. Yes, sir.
But it's a very delayed response. I don't understand. This is not a range application here, at least. Why such delay? I mean, students are sleeping still, or they are joining from their very cool comforts, you can say. So they are probably, I don't know how much they are trying to understand or listen also. And they are not probably very alert, you can say, as in the class. Normally they are. So in frequency hopping, I was just asking a question. At least as a communication engineer, you should obviously little bit having a understanding, like Bluetooth, which particular frequency it operates, why, what kind of technology there in Bluetooth. All of you are using Bluetooth now, you can say, speakers or everything in your house or even your mobile also. I see a lot of students, they are making use of this particular speakers now. So I mean, they while their mobile is in their pocket, they keep on talking, you can say. So, but at least as a technical, you can say, student, you must be having a curiosity how it is happening, what kind of Bluetooth, what is meaning of Bluetooth signal. No idea. Bluetooth signal, you can say, because this is operating at this particular frequency, because ISM band, this is a industrial scientific, you can say, medical band, which was reserved for, you can say, applications. I mean, this spectrum was not allocated for any, you can say, any designated application. So when somebody thought about this kind of idea, where he obviously he could not get a license, or you cannot go for a particular another frequency, you can say, band, where there were already, you can say, those band were allotted for different applications. So what somebody, you can say, amateur, some engineer, or you can say, he in the lab, he tried to work on this particular frequency range because he didn't need any license. And so they perhaps made it possible that when your signal can be easily transmitted at a short distance, communication for different application of the mobile. And he used this frequency hopping spread spectrum signal, so that this is very safe. And that is how, you can say, this Bluetooth came. I hope at least you should perhaps maybe read more about it. Maybe right now coding is on the priority, but along with coding, I think if you know about a little bit about hardware also, I think that will make you maybe a better engineer. A spread spectrum system technique, and this is, I mean, either AM or, I mean, PSK modulation. So what happens in frequency hopping is the whole spectrum we divide into number of, you can say, channels. Each channel is given a particular, you can say, band width, and all this, those particular, you can say, channels keep on switching on, you can say, hopping on from one frequency to another one. Now the, hopping may be very fast, hopping may be very slow, you can say, I mean, all your, every chip is taken by one, you can say, carrier, or, I mean, one chip may be carried by two carriers also. So that's very, you can say, fast. Or another example of that. Now, this signal to be frequency hopped is usually a BFSK signal through MRA FSK, MSK. That's what we use for hopping, can be employed. Considering that BFSK is used, we have original signal. You know about BFSK now. So I can represent my BFSK signal as omega 0 t dt sigma t plus theta, where dt is the data to be transmitted and fs modulation is then applied with some carrier. So I can do that. Here fs signal has a carrier frequency which changes the hopping rate fs. That means you might be wondering that what is, this hopping, who is deciding this hopping? The hopping is decided by the, again, your, like in CDMA we had a code. Here also we have a code. Code means essentially, I mean, you can say, that orthogonal codes that we talked about, that particular code here also determines the hopping pattern, that which frequency after that, which frequency. So, and the frequency change is so fast that it's very difficult for anyone to perhaps tape or anyone to capture that signal and recover this signal except the intended user. So this is again a very secure system. The frequency chosen, each TH is selected in a pseudo-random manner, as I said, through a PN sequence from a specified set of frequencies, typically 32 to 500 different frequency. As particular, you can see this spectrum we can go. The primary advantage of frequency hopped spectrum is that it enables the transmitter to change its carrier frequency and thereby avoid an otherwise in-band interfering signals. Okay, so whatever carrier you define on, it will switch on. We have, I think you've seen in M-array FSK, I mean, different, you can say, frequency you can transmit, different symbols you can transmit. So here also, I mean, different frequencies you are trying to use for your, you can say, information transmission. For example, consider that FS signal spends an equal time at each of the 1000 frequencies, F1 to 1000. That's how you can say bands you can decide on. Also assume that BFSK is employed. The FS rate of data is FB. Bandwidth used by the signal at any carrier frequency, that is obviously 4 FB. I mean, you can see the separation. Now assume that there is an interfering signal having a bandwidth B is equal to 4 FB and a fixed carrier frequency Fj. If frequency hopping were not employed, I mean, again, we are talking about some sort of interference or some jamming process. You can, I mean, indirectly say that if somebody is, trying to block a particular frequency, then because of the hopping, if frequency hopping were not employed and the interference were located in the transmitted signal's carrier frequency, then interfering signal power was sufficiently large for probability of error to be, I mean, can be made larger. Under these circumstances, we could do no better than to guess. In military systems, the interferer determines the signal's carrier frequency purposely, transmitted that frequency a block or jam, as I have explained like on last lecture. By employing FS and using say 1000 frequency, the probability of the same interferer causing an error is reduced by how much? 1 by 2000, because now my frequency is hopping, it's not getting transmitted at one frequency. So error is, reduced by 1 by 2000 or 1 by 2000, whatever the carrier. You should understand that, these particular carriers that you are having 1000, 2000, and that particular switching is changing so fast, you can say maybe more than 1500, switching per second or something, you can say. Okay, so it's very fast switching. Note that thermal noise is ignored, but you understand the concept that how frequency hopped spread spectrum system cannot be easily jammed also, blocked also, and maybe you can say no unauthorized user will be, you can say, access that signal. Suppose whatever you can say, even if you are transmitting, let's say, a song or a music to your friend, through Bluetooth, that's very safe. Nobody else can have, that kind of technology development has taken place. A probability of error is often considered to be very large and would render such a system useless for data transmission. As a result, FS system employs error correction coding to reduce the probability of error. As I said earlier on, even despite this particular reduction in error, this is still very high. So again, we have to make use of some, you can say, error correction also for probability of error. I hope you have understood it. Any student wants to ask any question? Please feel free to ask questions. Now, no near far problem is there in frequency hopped spread spectrum system, which was there in direct sequence spread spectrum. So there is no problem, no near far problem, as the frequencies are different. Obviously, you are making use of different frequencies. That I think we have already explained. I mean, 4FB is the, I mean, you can say the minimum bandwidth requirement for transmitting, you can say, corresponding to 1 bit in BFSK. So this is one, this is another one. So that's a spectrum you can calculate. And this is what, a system will look like. You can say this is my data. Then I have the FM modulation. FM modulation is put to, you can say, some carrier. I mean, some carrier I am getting modulated along with, you can say, corresponding to my signal. And I'm transmitting it corresponding to this VT signal. Of course, there will be some, you can say, corresponding to, I mean, that's the modulator part only. And if you, this modulator part, I mean, that is getting, input signal here along with the noise. What I do, I think the same thing you, perhaps if you, those of you who are present in the lecture, we discussed in the class also, like in offline lecture, that we will have two filters at particular two frequencies, and then each filter will give me a finite out depending upon which particular frequency has come. Okay, so that's the same thing. I think that BFSK modulation demodulation system, we have already seen that. Two modulators are combined into a single FM modulator using a frequency synthesizer. Major problem area in the use of is a synchronization. As I said earlier on, synchronization is a big problem because you want to have a high data transmission, and then there the clock synchronization is a big issue, because if that does not happen, it will be a problem, you can say. Now you might so far wondering also, what are the properties of this PN sequence? This PN sequence should have a certain property also. So how do you generate? One is, this, you can say, pseudo random sequence generator, linear feedback registers. So what is done is, you can say, you have the D1 D2 for flip-flops, and of course you can combine them through some parity generator, and this particular system will produce, you can say, corresponding to, of course, I mean, depending upon my, you can say, input, I can provide to some XOR gate. Now the clock is here, so the output obviously will be, you can say, different kind of output. This particular Q0, Q1 and Q2, they will different patterns will be there, and depending upon that I'll be getting my, you can say, corresponding to output. Now look how this works. For L is equal to 2 to the power n minus 1, and n is 1 2 3 4, how many you can say you have. So I can define them Q0 XORed with Q1. Likewise I can define, and then because if I have the 4 flip-flops, there will be 15 patterns. Okay, 2 to the power 4. So 2n minus 1, you can say, I mean, the 15 different patterns will be generated, 0 to 15, you can say. So I can, I mean, make use of this linear feedback shift registers. Clustering produced by the generator in figure when connected to maximum sequence length. Now, this PN sequences should have some property. One property is, you can say, it should be balanced. Balance means essentially, you can say, the 0 and 1 should be almost close together. That means 50% of that, 50% of that in any PN sequence. Then the periodicity also, like run length, how much run length, 0, how many runs it can have, you can say, corresponding to single digit, 2-digit clustered, 3-digit clustered. So that is, again, you can say, defined on what is the corresponding to this particular generation. And then, as I said, this how long it can be. It can be as high as perhaps you can handle on. So more length, you can say, more lengthy this PN sequence, more security will be to the signal. So I mean, this is you can see your PN sequence, and one such method is, now this sequences is not a unique, that sequences, if you look have studied in algebra, There may be maximum length sequence. There may be some other kind of sequences. Each sequence will have a different property, you can call it. So many sequences have been designed by the users to for applications in this spread spectrum system. As I said earlier on, I mean, whole spread spectrum is based upon autocorrelation. So the autocorrelation function RP and tau of PN sequence is what? A signal GT, correlated with a signal delayed by, you can say, tau. So that this expression, I think no student should have any problem, where GT assumes the values plus minus 1 volt. As might be expected, this RPN, this 0, this should be equal to 1, because autocorrelation value is maximum at 0. Understand? I think all of you know about it. We now calculate RPNT for T is equal to NTC. Okay, where N is integer. That means 0, it's okay. But at NTC, what happens? Let us say if I correlate at, you can say tau is equal to NTC. Okay, and GT T, I mean, corresponding to with the delay of NTC. So if you calculate that, now GT KTC is a PN sequence, and in the course of L chips, there is one more 1 than 0. Okay, hence the average value of G minus T is minus 1 upon L. Okay, as shown in finally, since the sequence has a period LTC, so it has R tau corresponding to, I can plot this RPN. If you plot, look here, 0 it will have maximum, and another at, you can say, more than 1 LTC. LTC means, I mean, the length that I am defining corresponding with the chip duration. This will again have, you can say, maximum here. So that's what this PN sequence is, you can say, corresponding to, as I said, PN sequence autocorrelation function is as good as your autocorrelation functions of a white noise, AWGN noise, additive white Gaussian noise. And that is why this is called a pseudo noise sequence. I hope you get it. Or you have any question? Please feel free to ask. It's an important concept, in fact, that how do you say that this is a pseudo noise sequence? What is the PST of PN sequence? Power spectral density. Power spectral density is a Fourier transform of RP and tau. Okay. Now this will consist of, you can say, corresponding to the delta pulses, and along with some sync function, you can say, corresponding to my GPN will be corresponding, I can define upon, if I plot f here, and I can define my V square upon L sin f plus JFC upon L. L is the length I am taking for my sequence. So depending upon that, I can define my, you can say, particular power spectral density of PN sequence. Synchronization, as I said earlier on, synchronization is a big issue in, of course, all communication systems, but more so in, you can say, spread spectrum, where the chips are, you can say, very, very small in duration, and any kind of delays in wireless particular media can be, you can say, problematic or will not produce correct results. So non-coherent communication systems such as FSK requires bit synchronizers to allow signal recovery at the receiver, even if you have a non-coherent communication system. Now, coherent system require in addition carrier and phase synchronization to permit the modulated signal to be mixed down to the baseband. I think you appreciate that, perhaps. What is the meaning of carrier and phase synchronization? That means both. I mean, phase synchronization is also necessary along with the, the frequency of your carrier also. In a spread spectrum system, a third synchronization is required to allow the regeneration at the receiver of a duplicate of a chipping waveform used at the transmitter. We consider succeeding section synchronization procedure for FH and, you can say, my DS spread spectrum systems. And the term acquisition is referred to as coarse synchronization, and tracking is used to refer fine synchronization. Okay, so how do you track it and how do you make it fine? So acquisition of FS signal. Okay, now look here, this is a acquisition circuit. Acquisition means I'm trying to, you can say, capture that signal. How it is happening, you can say, corresponding to, look here, this is my clock, this is my PN generator, and this is a frequency synthesizer. This is a transmitter. You can say I'm transmitting at a particular frequency. So this is my, you can say, transmitted output. So how do you capture it? Now suppose this is the signal that you are receiving. The signal is getting multiplied by, you can say, corresponding to output. You can say voltage control oscillator. Again, you are trying to acquire that same signal along with, you can say, phase and frequency. So how do you generate this phase and frequency signal? You band pass filter that we have done, envelope detector, because I mean obviously you have to have converted to some voltage, frequency variation is converted to voltage variation, and then you have a threshold voltage comparator. So it is either 1 or 0, and so depending upon that I calculate that particular, you can say, voltage, and then again I try to keep on feeding this particular input here for every, chip sequence. So this is acquisition means, I mean, that the same kind of, you can say, for synchronization you have to acquire, and then the acquisition of fs signal. Now this is my input signal frequency, this is my synthesizer output frequency. Understand meaning of synthesizer output frequency means, I mean, you can say rather estimated or calculated, frequency. And then this envelope detector output, where do I put, at least take my decisions. So that's the threshold voltage I decide upon. And then this is where your comparator output is, you can say, corresponding comparator output will be high here. If it is 1, you can say again it's a 1. And this is my controlled oscillator output. So depending upon controlled oscillator output, this particular frequency variation I can ensure. And this is again a tracking of fs signal, tracking as we have done in case of, you can say, our direct sequence spread spectrum systems. So tracking in frequency hop system can be also, you can say, through envelope detection, transmission, then VCO PN generator frequency. Again, I mean, tracking means this early gate tracking circuit. When you write the assignment, that's a very good, example for you, for the students who wants to at least study a little bit about early gate. That's one of the, standard this electronic circuit to synchronization. I mean, these particular signals. Similarly, this can be put on, I mean, the same thing put into this early gate waveforms. Acquisition of DS signals, again, this is the same thing, you can say, corresponding to, and maybe this, I think, let us look at it, I mean, maybe more carefully, you can say, corresponding to, I mean, we know it about at least what should be the input corresponding to here. Then this input feed it to your some sort of band pass filter, annular detection, and then this is the integrator. Integrator feeds to the comparator with this threshold voltage, and depending on this output here, this output, you will have a corresponding capacitive, and this whatever this input is there, this is your VCO output, clock pulses, okay, at a chip rate. And so depending upon these two, you generate a PN, you can say, corresponding to output here, this AND gate output that feeds to the PN generator, and it generates what is GT minus ITC corresponding, you can say, whatever the chip delays are there, that is produced, you can say, corresponding to here. So again, this is also a circuit for synchronizing this particular, and this is again, corresponding to more, you can say, a delay locked loop. Okay, you know about PLL. Similarly, you have delay lock, DLL also. That's used to track the DS signal. Okay, so how does a delay, you can say, works on a DLL? You can see this, that's the input coming input. I have, you can say, corresponding to my this sequence, that the delay input of, you can say, corresponding to my PN sequence that I multiply with. I get the output. I have a band pass filter, envelope detection. This is again goes to my, you can say, low pass filter, and then to the my voltage control oscillator. This voltage control oscillator then makes the modification, and then you can say, corresponding to, I have another, you can say, corresponding to, you can say, my HF BF filter, and then this particular, input, that input that I am getting here corresponding to this GT, because this is feeding is minus TC, this is plus TC by 2. And here I am getting my V input, and this is fed to again to my annual detection, and depending upon these two inputs, I feed it to, or I correct it through my voltage control oscillator. So that's what I think all of you have studied about PLL, phase lock loop. Similarly, this DLL is also used to, you can say, synchronize the corresponding, depending upon the variations we can see. So this is all I think today. We will start from here. I think there are not many slides in this particular case, I think, or maybe another, you can say, topic. I think this is over. Okay, probably nothing more in this particular, that's basically mathematically, you can say, at tau minus TC upon T, tau plus TC by 2. And these are the VD and VA signal that we are generating at the two blocks that's shown here, VA and VD. And if this is my input, these signals are passed through a identical band pass filter, each having a bandwidth of this thing. Each filter is much less than the bandwidth needed to transmit a PN sequence, and only average value of the product will be passed. So the file output will be this one, you can say, because we can easily verify that. And this is my VF, and corresponding to this is DF and EF. I can calculate both of them. They are almost identical, except there this chip delay is at where I have T minus TC and here T plus TC. So RGT, I calculate this particular G, T plus, tau plus, I mean this corresponding, and my envelope detection again produces, you can say, corresponding to V output, VD output in this form and V output in this form, and then I calculate VCO. Depending upon these two inputs, I calculate this VCO Y2, and that particular VCO decides, you can say, corresponding to, if you plot this, this is VCO input voltage YT. So if you have, you can say RJTT plus tau C, RJTT minus tau C, okay, the way you can see the particular chip, this particular two processes. One is the solid line, another one is corresponding to dotted line. And if you look at, this particular signal here, if you plot YT as, I mean, this particular signal difference of that, the variation will be something. So this minus TC by 2, you'll have peak, and for TC by 2, you'll have corresponding to peak. And this is how you can fire on and you can adjust the corresponding delays. So this is, I think, all I wanted to complete. I mean, of course, there are many other things I want to cover also in a spread spectrum, because the applications are many. Okay. So like, what is, fast hopping and what is slow hopping? So in case of slow hopping, I mean, each symbol, you can say, or each bit, you can say, is carried by, let's say, more than one frequencies. Okay, or maybe a one bit is carried by corresponding to the fast, hopping. That, I think, diagram or other things, if I got, in some, presentation or some transmission, you can see corresponding to slides, I'll again, you can say, make you perhaps more explain it. I mean, explain it in a perhaps maybe more simplified manner. Of course, it must be clear. I don't think there is any problem also right now. Other spread spectrum, you can say, applications, if you are interested a little bit, students who want to at least know more about it, then we can go for narrow band and wide band signal systems also. And then maybe you can say, corresponding to detection also, like multi-user detections or rake receivers, this kind of, things. But I'll see that. Let us see. I mean, let us first, finish the syllabus. Which other topic is remaining in our syllabus after spread spectrum? It's a link budget analysis, I think, probably. And maybe which other topic? Maybe some detection I would like to do more about it. Yes, students? Any question? I'll be transmitting these slides also to you. Maybe today I'll transmit this also slide to you. Okay? Yes or no?
Yes, sir.
Okay, sir.
You want these slides? Or you have the
Yes.
book? Or you have the book? If you have the book, all these slides are from the same book, Taub and Ceiling, the new version that has come up. Anyway, I'll be at least sending through my mail message all these particular slides. Okay.